Natural materials seldom occur in a form suitable for immediate practical use. The desired material is frequently chemically combined with unwanted elements, and the whole mineral is usually mixed with unwanted waste rock. The factor which determines whether a mineral is economically worth mining is its concentration in the rock. In this Cornish tin mine, the rich mineral appears as the blue veins. The rich mineral has to be broken away from the host rock, and at this stage, little attention is paid to the size of the rocks. As soon as the rock's broken away, this is the start of a long chain of events, culminating in the production of metals and other materials that you're familiar with. The first stage is mineral processing. This is where our story begins. Mineral processing is practiced by many industrial organizations and is widely studied in a number of university departments. There's an enormous variety of different techniques used to process minerals, but most of them have been developed using some of the simple physical and chemical concepts introduced in this course. This is a sample of the sort of minerals that are mined to produce many of the raw materials we use. The sizes are the sort that would appear on the surface. Some, such as asbestos and coal, can be used virtually as they're mined. Others, such as this chromium ore and a copper ore, contain the valuable mineral embedded in waste rock. Yet others, such as this copper, lead, zinc ore, contains three valuable minerals as well as the waste rock. So the job of a mineral processing engineer is to separate waste rock from valuable mineral, or to separate the valuable minerals from each other. To see how this is done, we've come down to the Mineral Processing Department at the Royal School of Mines in Imperial College London to see the sorts of techniques that are actually used. And the techniques we're going to look at are those based on density and viscosity that were introduced in Units 2 and 3 of the course. The first stage in the processing is to grind these rocks into a powder. This is a sample of the copper, lead, zinc ore ground into a fine powder, as you can see. But how can we separate the minerals in this powder? Well, here's a simple example. This is a mixture of sawdust and sand. If we tip it into water, we can see that the sand separates to the bottom, the sawdust floats on the surface. Now, why should this be? Well, in order to explain it, we need to consider the forces that are acting on the different particles. Let's have a look at it. Let's suppose that we have a particle of volume V and density rho s. The first force that acts on it is, of course, the weight, vertically downwards, W. And this is equal to the volume times the density of the solid times little g, the gravitational acceleration. When it's in a liquid, there is an upward force, the upthrust, and this is simply equal to the volume times the density of the liquid times little g, the gravitational acceleration. The resultant force acting downwards will be equal to W minus U, which is equal to Vg into rho s minus rho liquid. Now, as you can see, if the density of the solid is greater than the density of the liquid, this term will be positive, there will be a net downward force, and the particle will sink. On the other hand, if the density of the liquid is greater than the density of the solid, this term will be negative, so the downward force will be negative. In other words, there will be an upward force, and the particle will float. So if we're trying to find a method for separating two minerals using flotation, we want a liquid which has a density intermediate between the densities of the two solids. Now, the sawdust-sand mixture that we've been using in the earlier demonstration doesn't occur very often in nature. So let's look at some real minerals.
Here we have two real minerals. Let's see what happens when we put these in water. We have one very light mineral, diatomite, and quartz, which has sunk to the bottom. The diatomite has a density of 900 kilograms per meter cubed, whereas the quartz is nearly 3 times as dense. Now, we don't often have to separate this pair of minerals, but I have here a pair of minerals that we are frequently required to separate. This is galena, a sulfide of lead, which has a very high density, and this is the familiar quartz that we used before. Now, let's see what happens when we put these two in water. As expected, they both sink. If we want to use density to separate these two minerals, we must use a liquid of intermediate density. Watch what happens when I pour this into the separating funnel. Tetrabromoethane has a density of 2,900 kilograms per meter cubed, which is intermediate between the densities of these two minerals. As you can see, the quartz floats to the surface and the galena remains at the bottom of the flask. If I shake the flask to mix them up, there's no problem. They separate once again into a top layer of quartz and a bottom layer of galena. So, as you can see, the principle of density separation is very simple. All we have to do is to find a liquid of intermediate density, and then we can set up a continuous separation process.
The mixture of galena and quartz is fed to this vibrating spoon, which acts as a feeder for the separation process. The mixture falls into the separating vessel containing a liquid of density between that of galena and quartz. The quartz floats and is drained off along the pipe on the right. The galena sinks down the central funnel. The minerals are collected in separate filters and the liquid recycled back to the separating vessel. The flow rate is adjusted so that the quartz drains off in a steady trickle. The little black specks of galena settle to the bottom of the vessel. Because the liquid is recycled, a large quantity of mineral can be separated using only a small quantity of liquid. So density separation seems to be an attractive proposition, provided we can find a liquid with a density intermediate between the densities of the two minerals to be separated. But what sort of densities are we looking for? Most of the minerals of interest have densities lying between that of coal, 1,300 kilograms per cubic meter, and a lead ore, density about 7,500 kilograms per cubic meter. But what about liquids? Well, we have a range of liquids here. Each of these bottles contains 500 grams, and as you can see, because the density is different, the volumes are different. The lowest density, water, 1,000 kilograms per cubic meter. You can push that density up a little by dissolving some salts in it. Organic liquids, trichloroethane, density 1,300, or tetrabromoethane, density about 3,000 kilograms per cubic meter. Then Clarice's solution, an aqueous solution of a malonate and of phthalate, perhaps the limit of aqueous solutions, 4,300 kilograms per cubic meter. Then there's an enormous gap until you get to mercury with a density of about 13,500 kilograms per cubic meter. So in the range of densities we're interested in, there are very few liquids. Those that are there are either expensive or toxic or both. So it would appear that density separation is of only limited application. But wait a minute, look at this. Normally, coal with a density of 1,300 kilograms per cubic meter sinks in water. But what happens if something's mixed with the water?
Here I have a beaker of water with finely divided sand. The sand is kept in suspension by a stirrer, and the density of the resulting mixture is intermediate between that of sand and water. Watch what happens when I put a piece of coal in it. This coal has a density of 1,300 kilograms per meter cubed, and yet it floats on this mixture. If I switch off the stirrer, the sand and the water will separate into two layers, and the coal will sink down to the sand layer on the bottom. This idea is used in a commercial process called dense medium separation, and we have a pilot plant using this system in the main laboratory.
This small-scale industrial-type separator uses the same principles we've just seen in the laboratory. Again, it uses a sand-water mixture as the separating medium. A mixture of coal and shale from a hopper is fed by the vibrating feeder into a separating vessel which contains a dense medium having a density of about 1,400 kilograms per cubic meter. That is, intermediate between the densities of coal and shale. The coal floats into the right-hand channel and the medium drains back into the system. The shale sinks and is pumped back into the left-hand channel. Once again, the medium drains back for reuse. The whole operation is designed to be continuous, and similar plants are widely used by the National Coal Board for cleaning coal. The restriction in the use of this method is the maximum density of the dense medium. This is about 3,500 kilograms per cubic meter, and so is of only limited use in discriminating between any but a few of the metal-bearing minerals. So far, we've concentrated on trying to find a liquid that will float off mineral particles. And dense medium separation is a very good example of how you can make such a liquid using only water. But this isn't the only thing we can do. You remember this. It's diatomite, and it floats in water. What I've done is to break off some pieces. I'm going to grind them up. If I now put these into water, they sink. So although bulk diatomite floats, the rock making up the mineral doesn't. It's more dense than water. The reason is that in the large sample, there's a great deal of air trapped. So the bulk density of diatomite is less than that of water. We can use this on other minerals. If you can attach air to a mineral particle, then the combined density of the bubble and the mineral will be less than that of water. It'll rise to the surface, and so it can be used for separation. So can you attach an air bubble to a mineral particle? Whether a mineral particle attaches to a bubble depends on the nature of the surface of the particle. When the bubble touches the white mineral, nothing happens. But when it touches the black mineral, the particle becomes attached and can be lifted off the bottom of the vessel. No amount of trying will capture a white particle in the same way. This phenomenon has been adapted commercially to the separation of minerals such as copper and tin in a method known as froth flotation. Air is bubbled into a water tank containing the minerals to be separated, and one of them floats. In practice, a chemical is added which modifies the surface of one of the minerals. This is the mineral that attaches to the bubble and rises to the surface. The mineral contained in the surface froth is swept over the end of the tank and filtered to recover the enriched ore. So far, we've been concerned with whether a body will float or sink in a liquid. We've said nothing at all about how fast it moves. Well, let's have a look, using this simple demonstration, at what goes on when a body moves in a liquid. The density of the ball is exactly the same as the density of the liquid. So when immersed in the liquid, the ball should experience no net resultant force. The weight of the ball is balanced by the upthrust. So it doesn't matter where we place the ball in the liquid, it will stay stationary. Now, what happens when we throw the ball into the liquid? If the only forces acting on it are the weight and the upthrust, then when it enters the water, it should continue to travel at constant velocity because there are no forces acting on it. But as you can see, it comes to rest. This indicates that there must be some retarding force acting to slow it down. And it acts only while the ball's moving in the liquid, because once the ball has stopped, it doesn't start to move again in the upward direction. This additional force is the viscous force. When a particle moves, there's an additional force that we have to add to this equation. We're interested in the viscous force, which we can call F. The resultant downward force is now the weight force minus the upthrust minus the viscous force F. If the particle is a sphere of radius A, then Stokes' law says that F will be equal to 6 pi eta AV, where eta is the coefficient of viscosity, A is the radius, and V is the velocity. And therefore, the net resultant downward force will be that minus 6 pi eta AV. Now, I think you can see that if W is exactly balanced by U and F, then a particle moving in a liquid will experience no force. Therefore, it must move at constant speed. And this speed is called the terminal velocity. Well, let's see if terminal velocity can actually be measured. Let's drop a ball into a column of glycerin and measure the time to traverse 2 equal distances. Start the first watch. Start the second. And we measure the times for equal distances. Let's see that once again. First watch. Second watch. The times are roughly the same, so there is a terminal velocity. And if we know the distances between the marks, we could calculate its value. But different liquids have different viscosities. So the terminal velocity in water on the right is very much higher than that in glycerin. By the way, the air bubbles are also travelling at their terminal velocity. In just the same way, different particles in the same liquid will settle with different terminal velocities. We can exploit this to separate 2 different materials. If we apply a current counter to the natural direction of settling, and if this current lies between the terminal velocities of the 2 types of particles, then one type of particle will float and the other will sink. A continuous separation process could then be set up. The idea of viscous force is quite easy to understand, but what exactly causes it? Well, let's think about a thin film of liquid flowing over a solid plate. The liquid in contact with the plate must be travelling with 0 velocity. As it moves further and further away from the plate, the velocity will increase. At the surface, there'll be a slight drag because of the air, and so this velocity line will turn around. This line is called the velocity gradient. Now, we can use this as the basis for another form of separation. If we were to place a particle of that sort of size, it would move with a velocity determined by the velocity at that point in the liquid. On the other hand, if we had a larger particle, it would move with a much greater velocity determined by the velocity of the liquid at that point. And this is the basis of the shaking table. The shaking table is based on one of the earliest forms of prospecting, vanning. The technique is to swirl the mineral mixture around in a thin layer of water. The different minerals then separate into separate regions on the shovel or pan, in the hands of a skilled operator, that is. In the equivalent commercial process, a mixture, in this case a light and a dark mineral, are fed to the hopper of a shaking table. A continuous film of water separates the mixture into the band of light mineral on the right and the band of dark mineral higher up the table. In a full industrial scale process, as in this tin processing plant, the flow is adjusted so that the desired mineral flows over only one side of the table. No separation technique is 100% efficient at recovering all of the valuable mineral. So if the mineral is sufficiently valuable, the waste from one table is fed to a second table to recover yet further valuable mineral. All the methods we've looked at for separating minerals are used to a greater or lesser extent in practice. And I hope we've shown you how they're based on the very simple concepts of viscosity and density.